right now I want to talk about piecewise functions. What in the world does that mean? Well, a piecewise function is a function that uses pieces of different equations. An equation is a function. That's what that is. And we're going to use pieces of two different equations here. You see f of x, and that means y. That's the same thing as y. So y equals 3x plus 2, and y equals 5x minus 1. But I don't want the whole thing. I only want it to count for a certain set of values. So that's why we have these. These are like my range. Actually, I would say my domain. I apologize. These are my domain. They're what values you can plug in for x. They tell you which piece of the graph. I only want y equals 3x plus 2 whenever x is less than or equal to a 2. If x is greater than a 2, then I don't want to use that equation. I want to use this one. Y equals 5x minus 1 only when x is greater than 2. So what I always recommend to you in class is that you draw a line. It really helps visually. When you see those commas, draw a line, and that way you can kind of separate. Here's the range of values, my domain, and here are the equations that I'm going to be using. Now, here's a sample question of what would be asked. Find f of 6. What in the world does that mean? F of 6 means tell me what you get or what value you have when you plug a 6 in for x. Well, do I want to plug it in here or do I want to plug it in here? This is where we have to look at our domain, our set of values. 6. Is 6 less than or equal to 2? No, it's not. Is 6 greater than 2? Yes. So that's when I want to use the second equation. So what I'm going to do is I'm going to plug a 6 in for x. 5 times x, or 6 minus 1. And that is 30 minus 1, or 29. F of negative 3. New problem. When am I going to, or let me rephrase that, negative 3, is that less than 2 or is that greater than 2? Well, it's less than 2. So I'm going to plug a negative 3 into the first equation. 3 times negative 3 plus 2, which is negative 9 plus 2, or negative 7. If you have trouble adding and subtracting negatives and positives in your head, use a calculator to check your work. No silly mistakes. And show your work, because that's going to be very, very important. If you were to plug this into the wrong equation, if you show me the work, I can see at least what happened. And you also can learn where your mistake came from. F of 2. Now here's where it gets a little tricky. They both have a 2. So am I plugging into the first equation or the second equation? Notice how for each of these problems, the first thing I'm doing is looking to the right side of my line. I'm going to look over here and I'm going to check. And this side is going to tell me which equation I'm using. Am I using the top equation or the bottom equation? Well, 2 looks like it fits in both. However, the winner is the first equation because this says less than or equal to 2. So when we're equal to 2, we have to use that one. You do not get a choice. I'm going to plug it into 3x plus 2, which means 3 times 2 plus 2. And I get, whoops, I was jumping ahead in my mind, 8. 6 plus 2. All right? Now, this is a piecewise function, just kind of like your basic, generic, doesn't make it easy, but your basic piecewise function. There are different versions of piecewise functions. Believe it or not, an absolute value is a piecewise function. How come? Because you have a piece of one line and a piece of a different line coming together, making, if you remember, a V. So that's one type of piecewise function. Now, let's look at another. Greatest integer function. That is an example of a piecewise function. Next week, I am going to show you how to graph these. And you'll see that when we graph this, it's in pieces. It looks like a step of stairs. A set of stairs, a set of steps. All right. This is what the equation looks like. It has a double bracket. Now the double bracket means you're looking at a greatest integer function. What does that mean? It means, and I know it's hard to read, so I'll say it or read it. Give the greatest integer less than or equal to x. That's it. Tell me the greatest integer. What's an integer? An integer has no decimals or fractions. 1, 2, 3, 7, 12, 0, -2, -3, -58. Those are integers. So I want the greatest integer that is still less than the value that was given, or equal to. All right, so here's an example. If I were to plug in a 2.3, the greatest integer that is less than or equal to 2.3 would be 2. 8.89, you really want to say 9, but that's rounding. We are not rounding here, okay? The greatest integer less than or equal to 8.89 is 8. Now, you also at this point start to realize I'm not rounding, I'm just dropping the decimal. But that's not always the case, because let's look at the negatives. -4.4, I hope you can see this, I might move it down just a tad. Okay, -4.4, we would expect to get -4, but that's not the case. If you look at a graph, you can see -3, -4, -5. Where is -4.4? It's right about here. The greatest integer that is less than or equal to that value is not -4. -4 is larger. The answer is -5. So, let's answer some questions. I'll use, I don't see my green close by and I don't feel like getting up, so I'll use red. Okay. F of x equals the greatest integer function of x minus 5. All right? First of all, what happens when I plug in a 7.1? The greatest integer function of 7.1 is 7. But it wants me to subtract 5. And I get 2. Next is a 2.6. When I plug in a 2.6, I don't round up, I get 2. Greatest integer less than or equal to 2.6 is 2. When I subtract 5, though, I get -3. And here comes the one that's the trickiest. -6.8. If you need a graph, -6.8 is somewhere in between those two. The greatest integer, still less than that value, is not -6, it's -7. So it's -7, but don't forget we're subtracting 5, and I get -12. All right, that's pretty much it right now. Well, we'll deal with graphing later, but for right now, just making sure you understand how to plug it into a greatest integer function or just a regular piecewise function and be able to solve and find the values. All right, thank you. Good luck.